In today's video, we're looking at significant digits. We're going to go over the entire lesson. If you were already in class and learned about the basics of how to count digits, how to round off, and how to add or subtract, you can skip ahead to the end of this video where we talk about multiplying and dividing with significant digits. So significant digits apply to measurements. Anything that you've measured has a certain amount of uncertainty in it. For example, if you were to look at the length of a piece of copper wire and you were asked to tell us how long that wire is, you might just glance at it and estimate that it's 5 centimeters long. If you've estimated that it's 5 centimeters long, just by looking, that very rough measurement, that would have one significant digit. The number 5 is one significant digit in the measurement. On the other hand, you may have taken a ruler, maybe a simple ruler, and measured it again pretty quickly, and you came up with, no, it's actually 4.7 centimeters long. And now that you've got 4.7, we have two significant digits, the 4 and the 7, in that measurement. Now, with an extra significant digit, the second measurement is more accurate than the first. Now somebody comes along with a better ruler and they're more careful and they measure it and say, well, actually it's not 4.7, it's 4.73 centimeters long. So now that measurement has three significant digits. So the more significant digits you have in your measurement, the more accurate that measurement is. Okay? The less uncertainty there is in the measurement when you have more significant digits. So what we want to be able to do is look at a measurement, a reported measurement value, and decide, first of all, how many significant digits are in that measurement. In the examples up above, it seems pretty easy, 1 digit, 2 digits, or 3 digits, but it's not always that simple. The problem comes to the number, the digit 0. When a number or a measurement has zeros in it, they can be confusing. So let's take a look at the rules for counting significant digits in measurements. The first rule says that, as we saw up above, any non-zero digits in the measurement will always be considered significant. So digits like a 1 or a 2 or a 3, if they are not 0, they will always count as significant digits. The second rule says that if a measurement has leading zeros, so zeros that are at the beginning of the measurement, then they are never considered to be significant. So we look at this example, 0.0002 grams, and in that measurement we can see there's 1, 2, 3, 4 zeros at the beginning of that measurement. Those are all leading zeros at the start, so none of them are considered significant. The only significant digit is the number 2 because it's a non-zero digit. So that measurement has one significant digit in it. If you see zeros, the next rule, that are in between non-zero digits in the measurement, they will always count as being significant. So look at the next example, 0.002001 seconds. In that measurement, the 3 zeros at the beginning of the number are leading zeros, so they don't count as being significant. The 2 and the 1 are non-zero digits, so they will count. And then, as we just heard, if you see zeros in between non-zero digits, like these 2 zeros, then they do count as significant. So that measurement has 4 significant digits in it. Now, zeros at the end of a measurement, they're referred to sometimes as trailing zeros. These guys can be tricky. They can be a little bit confusing. Now, there's one set of rules, basically 2 rules that describe trailing zeros that are pretty common, but I'll come back at the end and tell you why I have a little bit of a problem with this common way of dealing with them. So commonly, you're told that if you see in the measurement a decimal point, so there is a decimal point visible in the measurement, then any trailing zeros, zeros at the end of the number, are considered to be significant. So for example, in this measurement here, 0.0200, we can see that the first two zeros we know are leading zeros, they don't count. The 2 will be significant. And then what about these two zeros at the end of the measurement? Well, because I can see the decimal point in the measurement, those two zeros that are trailing will count as significant digits. So that measurement, 0.0200 grams, would have 3 significant digits. Another example, if you see the number 20 liters, but it's written a little bit strangely, it has this decimal point visible, 20 with a decimal point, then we know the 2 is a non-zero digit. It is significant. And the 0 that comes next, a trailing 0, because I can see a decimal point, it will count as being significant. So a decimal that's visible in the measurement makes trailing zeros significant. Part B, if you do not see a decimal point in the measurement, then the rule that's commonly quoted would say the trailing zeros are not significant. But I think it's actually unclear. Okay, so let's take a look. Many textbooks, as I just mentioned, will say if you don't see a decimal point, the zeros are not considered to be significant. So many textbooks or websites or YouTube videos will say the number 5,000, because that measurement, 5,000 liters, has no visible decimal point in it, they would say only the 5 is considered significant. And we will use that rule a lot. So the zeros that are trailing here are not considered significant because there's no visible decimal. The reason I don't like that rule, or the reason I think it's ambiguous, is because these two parts, A and B, give us two options. Either all of the zeros are significant when you see a decimal, or none of the zeros are significant when you don't see a decimal. There's no option for anything in between. For example, how would you show that the 5 and the first 0 are significant, but the next two zeros are not? Well, you can't by that simple rule. How would you show the 5 and the first two zeros are significant, but the third 0 is not? You couldn't if you're dealing with just looking at a decimal point. So what I prefer to do is switch the measurement into scientific notation. So for example, the number 5,000 could be written as 5 times 10 to the power of 3. 10 to the power of 3 is 1,000. 5 times 10 to the 3 is 5,000. So that's scientific notation. In scientific notation, the times 10 to the 3 is not considered significant. It's simply telling you where to move the decimal place or how many places to move it. So in this measurement, the number 5 is significant. So this has one significant digit. It would be like writing 5,000 and not putting a decimal at the end. But if you wanted to say the first 0 after the 5 is significant, then you have another option. You could write 5.0 and then times 10 to the 3. Now, by the rule we saw earlier, because I see the decimal point here, this trailing 0 would count. So we have two significant digits. Times 10 to the 3 is not significant. So this would have two significant digits in the measurement. And we could keep going. We could put two zeros after the decimal, times 10 to the 3. Because there's a decimal visible, the 5 and the two trailing zeros count, and the times 10 to the 3 does not count. So that would have 3 significant digits. And finally, we could put the last 0 that was there, the third 0, also visible, times 10 to the 3. And now this number, again, because the decimal is visible, the trailing zeros would count. This would have 4 significant digits. So if you switch the number 5,000 into scientific notation, you could write it with 1, 2, 3, or 4 significant digits. But if you don't convert it to scientific notation, you have just two choices. You could leave the decimal off, 5,000, and you have one digit, or you could put the decimal in, 5,000, with the decimal present, and then all of the zeros would count. It would have 4 significant digits. So let's see if you can do this yourself. If you're checking your work at home, you can just skip ahead. If you are doing this for the first time, take your own worksheet and fill in the number of significant digits that are in each of these measurements. Or you could do this on a piece of loose leaf if you don't have the worksheet there with you. So 12.25, pause the video if you haven't done this, because I'm going to do them myself. You don't want to just watch me do it. 12.25, there are no zeros there, so all of those digits are significant. There's 4 significant digits. 0.017, the leading zeros are not significant. The 1 and the 7 are, so there are 2 significant digits. The next number, all of the leading zeros are not significant. The 1 is significant. And because I can see a decimal in the number, the 2 trailing zeros will count. So this has 3 significant digits. The next number is written in scientific notation. We see the times 10 to the minus 3 milliliters. The times 10 to the minus 3 we know is not significant, so we just look at the 2.90. The 2 and the 9 for sure, and then because the decimal is visible, 2.90, the trailing zero counts, so that has 3 significant digits. The next number, the leading zeros do not count. The 0 in the middle between non-zero digits does count, and because the decimal is visible, the trailing 0 will count, and of course the non-zero digits also count, so this has got 4 significant digits. 7,500, there's no decimal present, so we'll use the rule that says the trailing zeros don't count, and therefore it has 2 significant digits. The next number is in scientific notation again. The times 10 to the 4 does not count, so we just look at 8.0. The 0 there is a trailing 0. There's a decimal visible, so it will count, and so does the 8. So this has 2 significant digits. Zeros at the beginning of the number do not count. I see a decimal place, so therefore the 2 zeros at the end do count, and the 1 and the 5. So this has 4 significant digits. 4,000, I see a decimal. Therefore, all of the trailing zeros count. That would have 4 significant digits. 24,700 millimeters. There is no decimal point visible, so therefore the trailing zeros here do not count. Therefore, it has only 3 significant digits. All right, I'll stop there on this section. You can do the remaining questions there yourself and check them with the answer key or check them in class. Now, sometimes you've done a calculation on your calculator involving measured numbers. Maybe you've used the length and the width to find an area of a rectangle, or in this example, you've measured the radius of a circle and you've calculated its area. Your calculator gives you a number like this, 74.80250293. The calculator screen is just full of digits, and now you have to round off your answer. Well, instead of just asking your teacher, how do I round off the answer, or just guessing, we're going to do it based on a given number of significant digits. Now, for now, I'll just tell you how many significant digits to round off to, but later you'll do that yourself. You'll figure out in the question how many digits the answer should have, and then you would round off your answer. So, for example, in this question, if you needed 1 significant digit in the answer, you look up at the measurement 74.802 and you realize I need just 1 digit. That means you can keep the 7 as your only digit. So it was 74.8. The only way to do that would be to round that down, and you can call it 70. So you're going to just ignore all of the digits except the 7, And you can call it 70 without a decimal place, and now that would have just one sig fig, one significant figure. Now you could also switch that to scientific notation, round it off, and call it 7 times 10 to the 1. Every single answer could be written in scientific notation if you like, and some of the answers will have to be written in scientific notation. You won't have a choice to get the rounding correct. The second example, you want to keep 2 significant digits. So you look at 74.802 and you realize I can keep the 7 and one more digit. Now instead of saying 74, like some people might want to say, you have to look at the next decimal point, the next digit, which was an 8. So it's 74.8. So if we're going to keep just 2 digits, we have to round it up because of the 0.8. If it were 0.5, 0.6, 0.7, 0.8, or 0.9, we round up to 75. If it had been a 74.4, 74.3, 74.2, etc., you would round down and just call it 74. So because of that 8, we're going to call this 75 centimeters squared, or in scientific notation, 7.5 times 10 to the 1. If you can keep 3 digits, then the 7, the 4, and the 8 can be kept. The next digit is a 0, so the 8 does not get rounded up, it just stays as an 8. So we'll say 74.8, or in scientific notation, 7.48 times 10 to the 1. And lastly, if you wanted to keep 4 significant digits, then 7, 4, and the 8 and the 0, the next digit is a 2, so the 0 does not get rounded up, it just stays as a 0. So 74.80 has 4 significant digits. The 0 at the end would count because the decimal is visible, or in scientific notation, 7.480 times 10 to the power of 1. Now in your worksheet, the next page, there are, there's 20 questions. We'll do a handful of them together. There's a calculator display, a number that was on your calculator screen, and the number of significant digits you're allowed to keep. Round off your answer and put it in the box. You can put your answer in scientific notation if you like. You can leave it in standard notation, but remember, in some situations, you have to put scientific notation to get the number of digits. We'll see why in just a moment. So the first example, pause the video and do it yourself if you haven't already done it. So with 3 significant digits, we can keep the 1 and the 2, and then one more digit, which is a 1, so 12.1. The next digit is a 4, so that we don't need to round up. We'll just call it 12.1 is our answer with 3 significant digits. If somebody wanted to put that in scientific notation, 1.21 times 10 to the 1. The next one, we need to keep 3 significant digits, so the 2 and the 0, and the next 0. The next digit is a 4, so we don't round up. We'll just leave it as a 0. So 200. Now if I write 200 like this, it has only 1 significant digit. But if I put that decimal in so it's visible, now we have 3 significant digits. The zeros count at the end if the decimal is visible. In scientific notation, 2.00, again, those zeros are significant because the decimal is visible, times 10 to the power of 2. Now the next one is trickier. You can keep 4 significant digits. So we can keep the 1, the 7, the 3, and we can keep the first 0. But that's it. Well, there is another 0 before the decimal point. So there's no way to write this number in standard form, in the form that we've been doing here. The only way to write the answer here would be in scientific notation. So with 4 digits, we can say 1.730, those are my 4 digits, that 0 at the end counts because the decimal is visible, times 10 to the power of 4. So in that case, only scientific notation would be acceptable. The next one with 3 digits, we can keep 2.07. The next digit is a 0, so the 7 stays as it is. We don't have to round it up. Or, this is kind of strange, but you could write that in scientific notation, 2.07 times 10 to the 0. 10 to the 0 is 1. 2.07 times 1 is 2.07. Scientific notation is normally used for large numbers, like tens of thousands, hundreds of thousands, or bigger, or really, really small numbers. You don't usually use scientific notation to write 2.07. You could, as I just did right there, but it's not common. The next question, with 1 significant digit, that means only the 6. So you could write 60 and not include the decimal. That would have 1 significant digit. Or, in scientific notation, 6 times 10 to the 1. The next one has 2 significant digits, and we know none of the leading zeros count. So that means we can keep the 2 and the 7. The next digit is a 0, so the 7 does not get rounded up. So we could say 0.00027, or in scientific notation, 2.7 times 10 to the minus 4. And one more here that we'll do together, 2.902, etc., times 10 to the negative 12, and we can only keep 1 significant digit. Well, it's already in scientific notation, so I'm going to keep it in scientific notation. If I write it in standard form, that's going to be a really, really small number, 10 to the negative 12. It's going to have a whole bunch of zeros at the beginning, and I don't want to write that. So I'll keep it in scientific notation. I can keep 1 digit, but the digit after the 2 is a 9. That means we have to round the number 2 up, and we'll call it 3 times 10 to the negative 12. There's our 1 significant digit. Okay, so I'm going to stop there. I hope that helps. If you haven't finished, you can finish the rest of those examples. Some of them may be tricky, and you can ask about them either on Google Classroom or in class. Now, significant digits, you can count them, how many are in a certain measurement. You can round off a certain answer on a calculator, like we've just been doing, but you also need to be able to do mathematical operations like adding, subtracting, and multiplying and dividing using measured numbers. So that's what we're going to look at next. First, adding and subtracting. When you add and subtract with measurements, remember everything here is about using measured numbers, there's a rule that says we look at the number of decimal places that are in the numbers being added or subtracted. So when you're adding and subtracting, you actually do not look at significant digits. Instead, you look at decimal places to decide how to round off your answer. For example, 22.57 has 2 decimal places. The 0.57 are the digits after the decimal, so it has 2 decimal places. We're going to add 1.029, which has 3 decimal places. Then we're going to add 11.1, which has 1 decimal place. Now, if you grab a calculator and do that addition, the calculator will say this. It'll say 34.699 centimeters. Now, the rule for adding and subtracting is that your answer can keep only the smallest number of decimal places that were in the numbers being added or subtracted. Okay, so the answer has the same number of decimal places as the measurement that had the fewest. So if the first measurement here had 2 decimals, the second has 3, the third has 1, our answer can only have 1 decimal place, the smallest number. So even though it said 34.699, we would round that off to 1 decimal place and call it 34.7. The second example is a little bit easier because the very first measurement, 22 minutes, has no decimal places. If it has no decimal places, then I know that my final answer, rounded off to the smallest number of decimal places, will also have no decimal places. The second measurement here has 2 decimal places, the 0.02. The third measurement has 3 decimal places, the 0.757. When you add those on your calculator, your screen will say this, 26.777, but you can keep only no decimal places. So we have to round it off to a whole number, and we'll call it 27 minutes. The third example, the first measurement had 3 decimal places, the second has 2. When we add those together, the calculator is going to show you the number 10. That's all it's going to show, 10. But we need to keep the smallest number of decimal places, which in this case was 2. So we have to write this answer with 2 decimal places. But the calculator didn't show any decimal places. It just says 10. Therefore, we add zeros after the decimal point, and we say 10.00 so that it has 2 decimal places. Those were all addition examples. Let's do a subtraction example. If you take a dish with some liquid in it and measure the mass, you get this number here with 3 decimal places, 0.570. And after heating, though the liquid evaporates, the mass of the dry dish, after you heat it, is less because the liquid evaporated, and you wrote 15.070 grams, and it again has 3 decimal places. So since both of those numbers have 3 decimal places, we're going to subtract them to calculate the mass of liquid that evaporated. So during the heating, the liquid evaporated, and that's what caused the mass to go down. How much liquid evaporated? Well, we subtract. But we have to keep the same number of decimal places that were fewest in the calculation. So in this case, we're going to keep 3 decimal places. But if you actually subtract those two numbers, your calculator will say 7.5. But we need 3 decimal places. So we add 2 zeros to the end and say 7.500. All right? So those are the rules for adding and subtracting with measured numbers. There's another set of rules for multiplying and dividing with measured numbers. This rule is going to look not at decimal places, but at significant digits. And then you're going to round off your answer in the same way, that the answer can only have as many significant digits as the number in the calculation that had fewest. So for example, someone has measured the length and width of this rectangle. The length is 12.6 centimeters, the width is 6.4 centimeters, and we're going to calculate the area of the rectangle, which is length times width. So we're going to take the 6.4 and multiply by 12.6. Now this time we're not adding or subtracting, we're multiplying. So instead of looking at decimal places, we look at significant digits. 6.4 has 2 significant digits, while 12.6 has 3 significant digits. So when my calculator says that the answer is 80.64, that's what the calculator says, I look and say I need to round that off, so it has, let's look at those two choices, it's got to have 2 significant digits, the smaller number. So 80.64 needs to be rounded off to have just 2 significant digits, so we'll call it 81. There's a 6 after the 0, so the 0 gets rounded up, and we call it 81 square centimeters. Another example, you have a block 22 inches long there. It's 12 inches wide and it's 12 inches high. Well, we take those numbers, we're going to find the volume, so we do length times width times height. 12 inches times 12 inches times 22 inches. And again, we're multiplying these numbers together, so the rule says to look at the significant digits. This guy's got 2 significant digits, the next guy's got 2 significant digits, the next guy has 2 significant digits, So our answer can keep only two significant digits. So when our calculator says 3168, that's what the screen of your calculator would say if you multiply them together, we have to round it off to keep just two significant digits. One way to do that is with scientific notation. You could call it 3.2 times 10 to the power of 3 cubic inches. Now, another way to do it would be just to write 3200. 3168 would become 3200, but don't put a decimal at the end. If you don't put a decimal at the end, this will have two significant digits, and the zeros will not count. So 3200 cubic inches is another acceptable answer for that. One more example, we're going to calculate the density of this cube. Okay, a cube, the sides are all the same length, and we're told that the sides are 3.1 centimeters long. We're also told the mass, 32.718 grams, and we're going to find the density. Now you remember from grade 9 or middle school science, density is the mass of the cube divided by the volume of the cube. So let's calculate the volume first. The volume of a cube, length times width times height, or since those are all the same, you could say the side cubed. So we're going to take 3.1 centimeters times 3.1 centimeters times 3.1 centimeters, and our calculator gives us this, 29.79 cubic centimeters. Now technically, because 3.1 centimeters has only two significant digits, we should round the volume off to two significant digits. And if that's all we were finding, the volume, that's what we would do. And rounded to two significant digits, we would say it was 30 with a decimal cubic centimeters. Okay, that would be the volume if that's the only thing we're going to find. But we're going to go on and use the volume to find the density. So rather than round off the answer for the volume and then calculate density and round off again, so round off twice, I'm going to just take the answer for volume with its extra digits, the 29.79, and I'm going to round off once at the very end. Okay? So the density is the mass, 42.72 grams, divided by the volume, and we're keeping those extra digits right now. We grab our calculator. Let me see what the calculator said. 42.72 divided by 29.79. My calculator tells me that the answer is 1.4340, and it goes on. So that's what the calculator said. Now when you divide the mass by the volume, we have to keep the smallest number of significant digits. So we look at the mass on top, it has 4 significant digits, and then we look at the volume. But wait, the volume, we remember from the first part, should have had only 2 significant digits. So now I'm going to use that fact. Because the volume should have had only 2 significant digits, 4 digits divided by 2 digits, we're going to keep the smaller number 2 digits in our answer. So 1.434 gets rounded off to just have 2 significant digits, 1.4 grams per cubic centimeter. Now some people would have taken the number 30, they would have rounded off the volume in step 1 and put that in the second part to find the volume. I'm not going to have any problem with that, but it's actually better practice to do what I did here, keep extra digits in the first part and round off just once. If you round off multiple times in one question, you introduce what's called rounding error. And so this method eliminates the rounding error that we otherwise would have had. Okay? All right. Now remember, all that we've talked about here applies to measured numbers. Some numbers are also found in formulas, and they're considered to be pure numbers. They're exact numbers. They're not measurements, okay? Because they are pure numbers, exact, they can be considered to have infinite numbers of significant digits. So we actually don't look at them when we're trying to decide how to round off our answer. So for example, by definition, 1 inch, not 1.0, not 1.00, but 1 inch exactly, has 2.54 centimeters exactly. That's not measured. That's actual, both of those numbers are exact. So if you wanted to convert 6.3 inches to centimeters, and you're going to do that using what's called a unit multiplier, what we see here, we would take our 6.3 inches, and the way you use a unit multiplier, you take the units you don't want, inches, and you put those down here on the bottom of this fraction so that the inches divided by the inches will cancel. And then we put the units we want on top, centimeters. We're converting inches to centimeters. And then in this fraction, we take the recipe that we had on the side there. 1 inch, so I'll put a 1 beside inch, is 2.54 centimeters, so I'll put 2.54 beside centimeters. Now, on my calculator, 6.3 times 2.54 divided by 1 gives me, and on my calculator, let's see what we get, 6.3 times 2.54, we get on the calculator screen 16.002. But how many digits should we keep? Well, remember the 2.54 and the 1 that are in that unit multiplier, those are exact numbers. They're not measured. So don't use those to round off your answer. Just look at the 6.3 out front. It had 2 significant digits, so we're going to keep 2 significant digits and just say 16 centimeters is our answer. All right? So with pure numbers, perfect numbers, they have infinite significant digits. They'll never be used to round off the answer because they have infinite significant digits. All right, we'll do a couple of quick examples before we go. In question 1 here, I'd like you to cross out H and J because those involve scientific notation, and we're going to leave those out in this adding and subtracting question. So let's try question K just together here. So 41.025 centimeters minus 23.28 centimeters. You grab your calculator and subtract those. So 41.025 minus 43.7. Whoops, I just read the wrong number there. 41.025 minus 23.28. My calculator screen tells me the answer here is 17.745. Now remember, here we're subtracting. The rule for adding and subtracting was to round off the answer based on decimal places. So we see 3 decimal places in the first number, 2 decimal places in the second number, so I'm going to keep 2 decimal places, the smaller number. I'll call this 17.75. The 4 here gets rounded up to a 5 because the next digit is a 5, 6, 7, 8, or 9, right? It's a 5, so it makes the 4 get rounded up. 17.75 centimeters will be our answer. Okay, another one, let's try G down here. Pause the video and see if you can do that yourself. So 0.0653 plus 0.07654 plus 0.0432 equals, according to my calculator, 0.18504. That's what the calculator shows. But now we're adding measurements. So again, we focus on decimal places. The first measurement has 4 decimal places. The next one has 5 decimal places. And the last one has 4 decimal places. So we keep the smaller number. We're going to keep 4 decimal places in our answer. The next digit is a 4, so we do not round up the 0 here, and we'll call this 0.1850 grams. All right, so adding and subtracting, pretty straightforward. We'll go down to multiplying and dividing. Take a look at question 2A. Pause the video and try that yourself. So on my calculator, 2.89 times 6.01. This gives me, according to the calculator, 17.3689 centimeters times centimeters. This will be centimeters squared. It's like finding an area. Now, when you multiply numbers, we look at significant digits. So the first measurement there has 3 significant digits. The second number also has 3 significant digits, so we can keep only 3 significant digits in the answer. The smallest number here was 3 digits. So therefore, 17 point, the 3 is followed by a 6, so 17.4 square centimeters will be our answer. All right, take a look at number 2E and 2F. Take a look at this guy and this guy. Actually, let's do E, F, and G. So 5 times 5. Well, you want to say, without even a calculator, the answer is 25 in square centimeters. But the 5 and the 5, if those are measurements, they have only 1 significant digit each. So I can keep only 1 significant digit in my answer. Since it ends in a 5, we're going to round the 2 up, and we'll call this 30. And you don't put a decimal, and it has only 1 significant digit. So 30 square centimeters is the answer. Okay? 5 times 5 gives me 30, according to significant digits. Now the next example looks like the last one, but the first number there, 5, is not just a 5, it's a 5.0. So it actually has 2 significant digits now. The second 5 has only 1 significant digit. 5 times 5 is still going to be 25. And because it has only 1 significant digit in the second number, this is still going to be 30 without a decimal place. Can only keep 1 significant digit in our answer. But the third one, 5.0 times 5.0, this guy's got 2 significant digits multiplied by 2 significant digits, so we can now keep 2 significant digits in the answer. And when we get 25 kilometers squared, we can keep both of those digits because it's got 2 significant digits, and there's our answer, 25 square kilometers. All right, now I'll leave it there. Just one little word of warning. When you get to part N, okay, in part N, there's brackets on top with a subtraction. So what you're going to need to do there is you're going to need to first subtract those numbers. And don't round off your answer, but keep in mind how to write the answer when you subtract. We learned that earlier. Then divide by the number on the bottom, and when you get your answer to that, then think about how many significant digits you should keep in the answer, remembering the answer to the subtraction question and the answer in the number in the denominator. You can keep only the smaller number of significant digits when you've divided. Okay? You also notice that that letter N, as well as I and J and K, those guys all involve scientific notation in their numbers. If you're not sure how to use your calculator to do scientific notation, ask me that in class. There is a specific way to do scientific notation on a calculator. Make sure you learn how to do that if you're not sure. So you can complete now the adding, subtracting, the multiplying, dividing. Go ahead and also try question 3. You're going to calculate the density of these pellets based on the data in this table. So this is getting to a science-y kind of thing. Remember that density, as we saw earlier, is mass divided by volume. And once you've got the 3 densities for trial 1, 2, and 3, you're going to calculate the average density. You remember how to find average. You add up the 3 numbers and divide by 3. Okay? For question 4, let's leave that for now, unless you're very comfortable with unit multipliers. We can do question 4 together in class later. All right, so there's significant digits. how to count them, how to round off your answers, and how to add, subtract, and how to multiply and divide with measured values. And again, we're going to use those skills that we're learning in this little worksheet booklet all the way through the course. So be sure you can do this. You don't want to be losing half points throughout the course on all of your answers because you're rounding them off incorrectly. So I'll stop there. Good luck. Ask questions either through Google Classroom or in class if you're not sure about something.